We now discuss routing, and this involves 3 chapters on the DALI textbook, 2 different algorithms or types of routing, and then we'll cover how that's actually done, the mechanics of creating the route. So we'll start with what's called oblivious routing. As the name might suggest, it's oblivious to the environment. We don't care what's going on. We just route based on some fixed, predetermined algorithm. Okay, this can cause load imbalance because we're oblivious to that. Here's an exaggerated example. I have a ring, 8 nodes on the ring, and the traffic pattern is very simple. Everybody sends to 3 nodes down to the right. So 0 is sending to 3, and so on. And since the ring contains 8 nodes, going 3 steps to the right obviously is faster than going 5 steps to the left direction, wrap around from 0 to 7, right? So everybody would be doing that. And this is a this is a ring with bidirectional links, so you can send in both directions. Knowing that everybody is doing that, right? The counterclockwise links are completely unused. And this will create unnecessary congestion. As you can see, well, in this case, the pattern is so simple, then the load, the channel load, if you remember the notion gamma, is 3 for all of the right-going or clockwise channels, and 0 for the counterclockwise channel. So if every source node drop 1/3 the channel bandwidth for one of the channels, then the network gets completely clogged up. So load imbalance is the problem. When we don't care about what's happening in the entire system, we always pick whatever seems to be reasonable, then we may have a traffic pattern that gives us imbalance. And what do? Valiant proposed an algorithm. It's pretty interesting. The guy is called Valiant because, in my opinion, this is a very valiant approach, almost crazy. So he says, I have a network. If I want to send the packet from the current node to a destination, to make sure that my traffic is balanced, I would first send it to a completely random destination, a randomly selected node. Because of that, because it's randomly selected, that intermediate node becomes uniformly distributed. Okay? And then they are sending to a certain destination node, and then hopefully the traffic would utilize all the network channels available. So that may give you quite a bit of a balanced load, but it completely destroys locality. If I only want to send to my nearest neighbor, now in Valiant's algorithm, I may go to the edge of the network only to come back. So that's not a good idea, right? So you can immediately see that perhaps some modification to this is wise, and that's one version of it is minimal routing version of a Valiant algorithm that says, well, there is a box. Especially, this is especially obvious on Torus. You can have a bounding box. You have the source node and a destination node, okay, and that gives you a bounding box. Okay, this is 2D. Any n dimensional torus, you can draw the bounding cube if you wish. Then you say that I'm doing a random version of it within that bounding box. And on the right hand side, here is the explanation to all possibilities, to all examples. So let's see. The the label is this. The grayed out node is the intermediate node that I chose by random choice. So it can be 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, and 2, 1. Okay, these are all intermediate choices. Now, once you choose that, then you can do whatever you want. For instance, the bold route is choosing X first. So I will travel on the X dimension before I will turn until I reach the intermediate node. Now, since 0, 0 is the source node, and if you choose yourself to be the intermediate node, so this is already done. And you then proceed to go from the intermediate node to the destination node. And let's, for the sake of example, assume that the dashed is choosing Y direction first. So then the choice from 0 to 1 to 2, 1 would be following this route, Y first, and then finish up in the X direction. You can finish all of this, but we'll take maybe one more example. We choose 0, okay? No, sorry. We start from 0, we choose 1, 1 as the intermediate node, and we do X first to get there, and then we do Y first. In this case, there is no Y difference in the address, so we simply finish off the X route. So you see in this example, I have 6 different choices. They're all different. The routes are different. So if I toss a coin randomly, I would have 6 different ways of going from 0 to 2, 1, 0, 0 to 2, 1. And this hopefully randomizes the traffic, distribute them a bit more evenly. So that's very simple. Oblivious routing. I am not taking into account what the situation is. I try by construction to create a situation where I don't have to. This is the variant or variance of the variant approach. In contrast, I would adapt. I would make my decision based on what's happening. If I know some part of the network is congested, I try to avoid it. Okay, and how do I obtain this information? Well, you can obtain information via some additional services, just like when you subscribe to traffic information on your smartphone, and you can route around congested highway. But you have to build that network, right? In our case, then this digital network is the meta information network that allows us to make that adaptive decision. Okay? So if you don't have it, a very convenient piece of information is queue length, queue occupancy. So if I have a long queue and lots of packets are going out towards that direction onto that channel, then I know maybe that's more crowded. And if I have 2 equally useful choice, I can go through the left or the right, and the left is completely empty, I go that way. That's in a nutshell, that's really what adaptive routing is doing. So in theory, you say, well, that's smart. Like, people are emptying out of an auditorium, choose whichever door seems to be empty, that would balance the load. So theoretically, it's better than if people are doing this all obliviously. Oh, I'm going out of the left door. And if everybody think that way, too bad, we have congestion. But that's only theoretically, because in practice, the information you obtain may not necessarily be all that reflective of the underlying reality. So especially when you use queue occupancy, most adaptive routing that are in practice, at least those that I am aware of, reading articles, use queue occupancy. So they are propagating very slowly. Okay? Okay? It takes some channel to get congested before the upstream neighbor can start to queue up. And they don't queue up instantaneously. They queue up by having, because you don't get packet every cycle. This is not completely, so you get it every now and then. And so this delay propagates, it builds up, so your queue start to build up. And then at some point, you have to cut off your upstream neighbor from sending you more packet because you can't drain them into your downstream neighbor. So this propagates rather slowly, and we'll see a more exact example, an exaggerated one, but we can see this more quantitatively. So the information that you obtain doesn't propagate instantaneously to everyone, and it propagates slowly with a time delay. So in a sense, the information is only local. It's not global information, and that can lead to suboptimal decision. Whatever seems good in the local sense may be actually bad in the global sense. And again, we'll give you an example in the next slide. Okay, so how do you make it propagate faster? Well, if your queues are very shallow, that means if you get some congestion downstream, your queue quickly backs up, and you will therefore make your upstream neighbor, whoever wants to send you packets, more aware of the congestion. So that's usually called a stiff back pressure, right? I am back propagating this pressure very quickly. So shallow queues will give you that. But queues are sometimes useful. They handle network bursts very well. So in a way, if your network doesn't handle bursts very well, then adaptive routing is better for you. If your network handles bursts quite well, it has lots of buffers, then this local adaptive routing may actually be not as good. So here's the example. Let's look at the original example of a network. Now this time we just simplify it to two traffic flows. One from node 5 to 6 over here, and it's sending 1 packet a second. Okay, and that's exactly the channel throughput. So 5 is generating, this is a contrived example. So you being 3 over here, you want to send to 7. Okay, either direction is fine. You can go left, right, you don't know. And if you use Valiant's algorithm, you might send half to your left, half to your right before going on to 7. So in this example, suppose 3 is also sending at maximum speed 1 packet, 1 unit per cycle to 7. Then what happens? Imagine that, right? And if I were completely fair, I would allow 1 such packet to go from 5 to 6, 1 packet to go from 3 to 7, and suppose I have some queue. Then at 5, I would start to accumulate, because at 5, I get 2 sources, whatever 4 sent to me and whatever I generate locally. So I have 2 packets per second or per cycle. I can only send 1 per cycle, and therefore this queue would queue up. And let's say I have 3 entries in my buffer. Then after 3 cycles, my queue is completely backed up. So 4 will not be allowed to send me any packet. It will be allowed to send me a packet every other cycle. So therefore, at 4, my queue, and this is just the queue going to the right-hand direction, will also start to fill up gradually. It takes every other cycle to queue up 1 entry. So in 6 cycles, my queue becomes full. So you see this information back propagate to 3 in some time. It takes some time for 3 to even notice that there was congestion down the road. in that direction, and at that time it can choose to go in the other direction. Okay, so there's a delay in the propagation, and you can you can appreciate that you don't have global information. This is local information. It takes some time for you to know downstream neighbors' condition, and this can also be bad in tricking you into making suboptimal decisions. And here's again a contrived example, but these two nodes, this is the source, this is the destination. Okay, the congestion is symbolized by the thickness of the channel. So we have very congested channel over here, here. Okay, all these vertical going are very, very congested. And this one is slightly congested. This one over here between 1, 0, 1 and 0, 2. And if I use fully adaptive routing, by the time I arrive at 0, I have two choices. I can go north or west, east actually, to the right. And they're both going in the right direction. And I use my heuristic. This one is more the north, the upgoing direction is more congested, so let's go in that direction, not knowing that I'm ended up with even worse choices down the road. I have no choice because I'm already here. I wouldn't want to go back. I'm already here. Going back would be a bad idea because it takes longer. So that makes you think, okay, maybe going around with some detour is actually a good idea. And people have talked about that. So a minimum adaptive routing says, I'm doing adaptive routing, but I still want minimum routes. Fully adaptive routing says, okay, detours may be a good idea, even though it sounds longer, but you have less time waiting. Okay. So in minimum adaptive routing, in this example over here, from 0, 0 to go to 1, 2, minimum adaptive routing would be fine. At 0, 1, we would know to turn right. But a minimum adaptive routing would not work for this situation. From 2, 0 to go to 2, 3, we would not know because going this way is increasing the distance to the destination. And if you allow that to happen, if you really want to go by, and this does seem like a good idea if we have this global view, and this is called fully adaptive routing. Okay, so we allow detour, which is termed misrouting. So this is the misroute. This over here is what we call misrouting. We're sending it into a node that does not reduce the distance to the destination. Okay, now is misrouting, is global fully adaptive routing a good idea? Not necessarily. You have to be careful. Let's say I have this situation, again a contrived example, starting again from 0, 0, and I want to go to 0, 3. Okay, when I arrive at 0, 2, I find the upgoing direction to be congested. Okay, I have the notion that maybe I can perhaps go around it like that. Okay, but once like that, perhaps this is more visible. But once I get to 1, 2, look what happened. Both upgoing and forward going direction are very congested. So I may decide, well, let's then go in this direction. It's a misroute. Okay, when you look at it, it's going away from the destination, but fully adaptive routing allow you to do that. But if you're not careful, you may end up just keep on doing this loop simply because, oh, this is not congested, but it's not helping your cause, right? Now, of course, you need to prevent this from happening, and you may have to carry information with the packet to say, I've been misrouted the X number of times, so next time when I get a route, it would be regardless of congestion, I would go in the correct direction. So it's not a trivial thing. You have to balance. If you want a very simple decision, it may be suboptimal, and if you want the decision to be robust, you may have to add a whole bunch of support. So how does this stack up against each other? Here is the graph that I showed you early on. At the x-axis, we're showing offer traffic. Every node simply dumps some request to the node, to the routers, to say, I want to send this to the destination. And it depends on the traffic pattern, okay? And this is a very common thing that the network community people have studied. They use these stock traffic patterns. Why? I think it's just simple. It's simple, it's easy to understand. It does not necessarily reflect typical traffic, but the practice stuck. If you did it in your paper, other people would copy the methodology and use the same, and before long it becomes the common practice. Whether it makes sense or not, perhaps is forgotten. So this is a very common thing. People use this transpose traffic pattern where if you are in node ij, you want to go to node ji. Admittedly, this does happen in certain applications, but I personally find that using this kind of special micro benchmark is perhaps more dangerous than it is good. But anyway, in this example, and you can read up the detail in chapter 25, this is in the Dali textbook, we try these different approaches. What are the different approaches? We can have a complete oblivious routing, and the very common one is called dimension ordered. I go X dimension until I reach the correct column before I turn to the Y dimension. It's dimension order, very simple. You can go variant algorithm, which means I'm sending to a random location before I continue with, let's say, dimension ordered routing to my destination. Minimum adaptive is the thing that we show here. Okay, it's minimum adaptive, it's what we show here, that we will not misroute, like in this example, we will not misroute, but if everything being equal, we will choose the lightly loaded, the channel with fewer packets in the queue than the one with more packets in the queue. So that's minimum adaptive routing. Oops. And finally, we have randomized minimal, and this is this example over here. So we choose the box, it's randomized, and it's within minimal box, so we will never have misroutes. We will never go outside the box. So we compare these four. So what is a good curve? A good curve hugs the axis. That means it's low latency, and it can support a lot of traffic until it saturates. Okay, so that's the idea. Now let's look at this and see what makes sense, what is good. So you can already tell. Let's think about Valiant, which is a little bit hard to see. It should be this one with a little dot with a dashed line. So it's this one over here. That's Valiant on the right hand side, and this one on the left hand side. Okay, so it was a crazy idea in a way, yes, because I'm sending my packet to a completely random location in the network and then asking that node to send it to my destination. This almost doubles the traffic. right? It's two separate trips. I'm going to one node that has nothing to do with my destination, and I'm creating therefore a subsequent command, a demand to go from that location to my destination. And indeed, if my traffic pattern is benign, and one of the most benign traffic pattern is uniform random traffic, then you can see I saturate very easily, okay? Almost half of a simple algorithm that is dimension ordered DOR, dimension ordered routing. Okay, and it's also slower, takes more time, you know, than everything else. Okay, so this is bad if you have a good traffic pattern when you're looking at Valiant. But if you look at this very odd traffic pattern, and this is perhaps taken out just to show you, you see Valiant is not very bad. At least it saturates less or later than this, which is randomized. Randomized suffered from that because it's a oblivious routing. There are certain congestions. We're not avoiding it. Yes, at low load, our latency was good, but at some point when the network gets congested, the behavior is really terrible. All of a sudden, boom. Our latency goes up very quickly, and the amount of traffic we can sustain is very small. So Valiant buys you that robustness in a way. Okay, in a good case, it sucks in a good case, and it doesn't suck anymore in a bad case almost. But you can see, all is not lost if you have just some other mechanism. The randomized minimal, which is this dotted line. Okay, that line is pretty good. It's better than both. And over here, it's also in a reasonably good locate. It's slightly worse than dimension order routing, but in exchange, you get better behavior when it's an adversarial traffic pattern. And the situation is slightly more different for the minimum adaptive. The adaptive algorithm is the one thing that's left. Maybe I should change a different color. Let's use yellow. Is it visible? Oh, okay. That has to be. Then the minimum adaptive algorithm is this one, the highlighted version over here, compared to the one over there. So again, for the extra benefit in adversarial situation, I kind of suffer in the good case situation. So it's not always like that. I think the exact difference in performance, but the general thing seems to be that usually when you get some feature, you pay certain a price. So that's the message here. Okay, so that's the two types of algorithm. Very poorly designed, simplistic, oblivious versus adaptive algorithm. You see what you get. Okay, oblivious one is really good because it's simple. It doesn't try to do anything fancy. But when it sees bad traffic pattern, that's when it hurts you. And so adding adaptation can be a good idea, but it usually comes at some cost in a already good traffic pattern. So it's not an easy job to do. So we have these two different types. It's when you're designing the system, you have to take the traffic pattern, you have to understand what you're doing, what you're dealing with, and then pick perhaps the right choice for the system that you're designing. Now, this is general discussion. We want to do this type of routing, we want to do that type of routing. Now let's look at how this is actually done. How do we route? How do we make a decision the packet goes out this channel versus that channel. The very first one that you would think about is something probably because you know how internet works, is a table-based routing. You have a table. Let me change the color. I have a table. It writes these following pre-computed decisions in the table. Each table, the table is indexed by source node and destination node. Okay, and we'll see that this doesn't have to be the source. It could be from the current node to the next step. So this would be one portion of the entire route, but it's indexed by source node and destination node. So if you have n nodes, then it would be an n by n table. And obviously in most internet implementations, a lot of the routes share the same node, so you have don't care bits. So it's not an exact n by n. A lot of them are consolidated into one entry that says it matches many different sources and destinations. And the result of that table is maps to a subset of all possible paths. Okay, so P is a path, and this P, fancy P, is the superset of all possible paths. So this is a projection from n by n, your source destination tuple, to a subset of all possible route that you choose. This can be done at different locations. It can be done at the very source when you inject a packet into the network. Okay, and you're doing it just once. You are already figuring out, I want to go from here to there, and the intermediate path is ABC, and the rest of the route you're just following the predetermined routing. So this obviously does not fit very well with adaptive routing, right? Because you're already making up your mind before you can see some of the conditions along the route. So this doesn't have to be the case. You don't have to route everything at the source. You can route it at every node. So you chart the routing table at every node. In between the two extremes, you can check it every now and then. You check once, and that routes for the next 4 stops, and before you have to check again. So it's really a complete spectrum. Okay. This might be better suited for adaptive routing. Okay. And this is what is actually used in wide area network. Okay? You would go to the next node, figure out what you want, and do something. In computer-based network, we'll see one example, one product example. This is usually done for the next m hops, m being an integer greater than 1. Okay, so that's something in between source routing and per node routing. Okay. And finally, the route table is not necessarily all very specific X, Y, and then the route is this. You may have these don't care bits, which is why when you're doing a search, you have a destination, you want to match the destination. It's not an index operation, it's a search operation. And this is a content addressable memory, okay? Because I have the content, I don't know which entry. So that's called content addressable. In typical content addressable, I have my content, I want to match exactly what the content is in the table, and that's a search. So it's a binary content addressable memory because the value can be 0 and 1. But if I have a don't care bits that says, okay, as long as your first 3 bits are 0, 1, 0, you're going west, then you actually need what's called a ternary cam that can distinguish between 0, 1, and don't care. Okay, so ternary cam is a thing. It's a special type of chip that some companies, it's a very small market, it's not a household item. It's used in these internet routers. So, but some companies specialize in that. I think it was a Japanese company. So that's routing table. You have sort of all these different possibilities, source, node, somewhere in between, but it's usually just look up some table. It's not necessarily index. It could be content addressable, but it's a table nonetheless. But that's not all. You can have just no table. You're just computing this with logic. Okay. In a torus network, this is very easy to understand. For instance, dimension order routing. Well, what's my current coordinate? If I'm not done in the x direction, I will keep on going in the right direction until I get to the column, and then I'll go on the y direction. Very easy. You don't need tables. And that can be something like this. And this is showing a two-dimensional case where my choice can be go in the positive direction of x, negative direction of x, or the same thing with y direction, or I'm done. Right? And you could, in this case, generate the decision purely based on where you are, but also based on traffic, based on congestion. The Q lens can help you choose. But here's the example, right? So I have my delta stored in my route. So let's say I'm in 0, 0, and I want to go to 2, 2. Well, very easy. Then my delta is positive 2 and positive 2. So x would indicate the delta. This sign indicates the direction of it. Okay. So now the logic is fairly simple. Am I there in that direction? Okay. If it's 0, then that means I'm done. So this line over here would indicate I am done. If I am done, I wouldn't choose plus x or minus x. Okay, so that's where I have this inverted result driving my AND gate. If I'm done in x, then plus x or minus x would not be good choices. If I'm done with y, same thing, then plus y and minus y wouldn't be good choices. Then the only good choice is I'm there. I'm going to exit. If not, okay, if I'm not 0, this is not true, then what happens is I may choose, so this bit here is 0, so both these input to the AND gate are 1. For let's pretend we're dealing with x not being 0, then it's just based on sign. If sign is 0, that's positive, then I want to go into the positive x because that is 1. So that's a productive direction. If a sign is negative, then minus x is a positive direction. So if I'm not there and both x and y, the two deltas, are not 0, then I may get two choices. I may get a positive x direction and a minus y direction, and based on the Q lens, I can decide which one to go. And that's a algorithmic routing. Sorry about that. If you have 3 dimensions, you just have 2 more. And if you have n dimensions, you have 2n plus 1. And that's fairly simple. No table needed. Of course, after you route, you have to change the header to be carried with you to the next stage. So that's really it. It's in principle fairly simple. Again, we have 2 types of routing, oblivious and adaptive. And they can be done with logic or with table reading. Let's see how this is done in real world. We have 2 examples. They're fairly interesting. These are old, big supercomputers. One of them produced by IBM called SP2. It's a message passing machine. It's not a shared memory multiprocessor. Because the reason these type of machines are studied for network is usually they are large. message processing machines scale much better. We don't have to provide the many consider to be expensive cache coherence. What they're really selling, back then they actually have a machine called the RS6000 personal workstation or desk side workstation. So SP2 is really a machine based on these workstations, and it's a glorified cluster, not your typical Beowulf cluster where you buy a few I don't know, commodity Dell or HP rack-based server and then hook them up with Ethernet. They have their specialized network or router cabinet. So that's IBM's SP2 on the left-hand side. The right-hand side is a machine from a company that unfortunately that went down. I can't remember if they got bought up or they just died off. It's a Thinking Machine company. They have different types of machine, all called connection machine. The company is called Thinking Machine Corporation, TMC. The product line, the models are CM2, CM5, connection machine. And they use Spark. Of course, IBM uses their own PowerPC. And they use flight topology. CM5 use the fat tree or FortiClaw, fancy name. SP is somewhat different. We'll see. It depends on the size. And in CM5, the routing was adaptive. In SP, it's oblivious. So we see both done in practice. So let's talk about SP2 first. You have a machine in a frame. A frame is a rack. Okay? It's a cabinet, whatever you want to call it. Inside, you have 16 nodes. These are really just 16 workstations. And then they have a switch module. Today, in today's world, you go to build your data center, these would be called a top-of-the-rack router, or TOR, top-of-the-rack router. But they call it a switch module. This switch module has 64 ports. Okay, it's really 32 bidirectional ports. Okay. So if we can look at how this is done, maybe a little bit here, it's 32 by 32 bidirectional. Okay, but then you can think about it as having 32 input ports and 32 output ports, making it 64 ports. Whatever you want to think about it. So you have 32 bidirectional ports. So now, how do you connect them? This would be your 32 bidirectional ports. It's not necessarily in one chip, okay? It's right here. That's connected to a machine. So left-hand side, you can see each module has four channels, links, times 4. So there's 16 on this side and 16 on that side. These are bidirectional. So that's your 32 port switch module, and they're connected in this way. So if you want to talk within a cabinet, anybody talk to anybody within a cabinet, well, you go to one of the switch module, and then you can go on to the destination module. And so this leaves a couple of wires or channels hanging for the frame. So if you take a frame as perspective, then you get 16 bidirectional links going out. So that allows you to make all-to-all connection in a small case. If you just have 2 frames, it's not shown over here, then you have frame 1, you have frame 2, and you have 16 ports connecting them. You just connect them together. So this would be 16 channels at whatever speed per channel. And if you have 3 to connect, this is the solution. Okay? You give 8 to each other, to each of the other 2 frames, and it's fully connected. And you can keep on going, and if you have 5 frames altogether, this is how you connect them. You still have 4 to each frame. and then you have your connection. So the 32 port module is really built out of a smaller switch. Okay, so remember that we talked about this. If I want kn by kn crossbar made out of smaller ones, so it's k square n by n, and that's exactly what's happening. You have oh, by the way, sorry, this is not a complete crossbar. So it was made out of n by m, but it wasn't a crossbar topology, so you don't need k squared. Sorry about that. It was made out of 8 by 8 crossbar, and if they have 16 of them, they would made a complete switch, but it's not. It's a 32 by 32 switch made in this fashion. Okay, so you have the input ports, or one side, I shouldn't call it input, one side connected to your processors, the other side that's left out to be connected to another chassis. Okay, each of the switch is 8 port in the sense that they have 8 bidirectional ports, 0 to 7, as you see here. You can think about it as 16 ports, 8 input, 8 output. It doesn't really matter. It's really the same thing. So if you have more frames, then they would use a factory or folded close. So here's what happens. You would buy specialized switch modules. So this may all be housed in one frame. That's fine. These will be your regular frame. Each one of them contains 16 machines. And so in this configuration, we have 512 machines. There are 32 of these frames. Remember, each one has 32 ports going out, and no, not 32, 16 ports going out. Yes, 16 ports going out. There you go. 16 ports. That's what allows you to connect to 16 switch modules. Okay, so one to switch module 1, another to switch module 0, 1, and so on. So the maximum you can connect is 16 by 32, and that's 512 nodes. Now, if you buy something smaller than that, let's say I want 16 of those, then you double up. Okay, so I don't know, you have this switch module 1 being doubly connected to one frame. Suppose you have 0 to 15, and that would give you the 12, the 16, the 32 together. You would occupy the 32 ports. So that's the topology of the machine. In smaller machines, they're fully connected. This is not a folded close. There's no root. This is really just a star connection. In larger machines, you have a folded close. It's a tree. In some cases, a fat tree, because the root was multiply connected to. In some cases, it's not a fat tree, it's just a tree. And when you are routing, you do this following thing. Okay, this is a routing table. Well, we're not drawing the routing table. Routing table is somewhere. You check the routing table, and you would read 4 routes possible from the routing table. So if you, let's say you're going from X to Y, here would be route 1, route 2, and so on. Okay, you have 4 routes stored in the routing table. Each one actually has a counter associated with it. So if I encountered a packet that wants to go from X to Y, and I would choose one of the route, and I would increment the counter. This means I've done this. So if I look at the counter, I know which one was used. So I can randomize. The route is stored in the header of the packet. That's right here. This is my packet. It will have payload down there, the data, and it will store a couple of steps or routes of what we should do. Okay, and once we take this route, we'll put it in the packet, and when we will send it on its way, and we will know what to do for the next couple of stages. And if the machine is not big enough, then this might be already what you it may be already all that you need to do, and it becomes really source routing. So that's IBM's SP2. Here is somewhat similar, but they connect it slightly differently. But it's also a butterfly, or folded claw rather. It's a fly. It's the same type of a switch, 8x8, 4 bidirectional links, or eight ports. They use these type of machines. All these boxes that you're seeing over here, they are 8x8 routers. So you have 4 bidirectional links going in, and then you have 4 bidirectional links going out. The interesting thing is when they're connecting it, the going out, the bidirectional link going out, only 2 of the ports are being used. So this would be your root level. At the root level, each router is connected to 4 nodes, but they're redundantly connected to 2 routers. Okay, so that gives you path diversity. You can pick any one, it doesn't matter. And these leaf nodes are connected to the next level of the root, to the next level of the root, and so on and so forth. So you can have level 2, level 3, until the end. That becomes the real root. So how do you route? Well, this is a tree. So you know who you are, you know who the destination is, and therefore you know the least common ancestor or the least common root. Okay, if it is this node over here, if it's this node over here, wanting to connect to that node, your common root is this one over here. Then you just have to go there and go there upstream and go downstream, right? So the upstream is routed adaptively. Remember, each node has 2 possible upgoing route, and this applies recursively. So each level 1 router has 2 upstream routes. Anyone would do. Okay, this is completely just route diversity. There is no fixed. There's no unique path. You can keep on choosing different ones until you reach a particular node. However, a particular route. However, going downstream, that's only one. There's a unique. You can't do adaptive routing. It's just a fixed route. The downstream is unique, and therefore you have no choice. So that's about it. It's 2 different machines. One use random routing, randomized routing, picking among 4 possible choices. Another uses adaptive routing, okay, based on the uplinks congestion. So both are used. In both cases, they're using fly topology, and they can connect to quite a lot of machine in both cases, on the orders of thousands. And so that's routing with the examples, and next time we'll look at flow control.